welcome friends. Today in this video we are discussing about dipole in uniform magnetic field. Okay, first we need to know what is uniform magnetic field. Okay, so as I told you in a previous video, I have explained what is uniform magnetic field and what is non-uniform magnetic field. Here uniform magnetic field means it is a region in which magnitude and direction of magnetic field is same at all points. Okay, so and then how to represent uniform magnetic field by using the arrows. So the parallel arrows, so that are equidistance, that represents the uniform magnetic field. Uniform magnetic field. So here the magnitude of magnetic field and the direction of magnetic field is same at all points. Okay, you look here and you look here and look here. So magnetic field is same and magnitude of magnetic field as well as the direction of magnetic field is same at all points. So next, here we are keeping or we are placing a dipole. Which dipole? Compass needle here, magnetic compass needle in uniform magnetic field. Okay, so what happens to that dipole or compass needle when we place that needle or compass needle in a uniform magnetic field? Okay, so first, so this is my uniform magnetic field. So this line represents magnetic field is uniform. Okay, so next I need to place one magnetic needle. Okay, so this is our magnetic needle, compass needle. This is our yes and this is yes. North and south. Okay, the magnetic field strength is B and this compass needle magnetic dipole moment M. So M is the small letter M is the magnetic dipole moment of this magnetic compass needle and tau. Inside this torque. Okay, torque is acting on this magnetic needle and here R is the moment of inertia. Here R is the moment of inertia of this compass needle. Okay, so these are the things we need to know what happens when we keep this magnetic compass needle in a uniform magnetic field. Okay, so next is I need to know here this is my magnetic field of strength B. So B is the magnetic field strength and I am placing this magnetic compass needle in a uniform magnetic field. So this compass needle has magnetic dipole moment M and I know the magnetic dipole moment of this compass needle, that is M, and I know the moment of inertia of this compass needle. Okay, so next I want to know what is the torque acting here. Okay, what's the torque? How much of torque is acting on this compass needle when we keep the dipole in a uniform magnetic field. So this is our dipole, right? S and L pole. So then this is our dipole and we are keeping this magnetic compass needle in a uniform magnetic field, right? And next is, so next I need to know how much torque is acting on this compass needle. So here the torque is acting on this compass needle. This torque result in oscillation of this magnetic needle. Okay, so torque means here torque is a force. Okay, forces which acts in the opposite direction or in the like this. So this is my force. The force F1 is acting in downward direction and F2 is acting at two directions. So here we see torque, in the sense the rotation of this whatever this thing. Okay, so this is our anything. Okay, consider this is the dipole. So this is yes and this is yes. Okay, So this is N and this is S. So here F1 is a force acting downward and F2 is a force acting upward. So here the torque acts on this magnetic compass needle that results in oscillation of this compass needle. Okay. So torque means here is a forces which acts in different lines because a rotation of this magnetic compass needle. Right. So torque ಅಂದ್ರೆ ಏನು ಹೇಳ್ತೀವಿ ಇಲ್ಲಿ ಫೋರ್ಸ್ ಯಾವ ತರ ಆಕ್ಟ್ ಆಗ್ತಾ ಇದೆ ಅಪೋಸಿಟ್ ಲೈನ್ ಅಲ್ಲಿ ಆಕ್ಟ್ ಆಗ್ತಾ ಇದೆ ಅಪೋಸಿಟ್ ಲೈನ್ ಇನ್ ದಿ ಸೆನ್ಸ್ ಒಂದು ಅಪ್ವರ್ಡ್ ಆಗ್ತಾ ಇದೆ ಇನ್ನೊಂದು ಡೌನ್ವರ್ಡ್ ಆಗ್ತಾ ಇದೆ ಅಂತಂದ್ರೆ ಸೊ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ ಆ ಆಬ್ಜೆಕ್ಟ್ ಅನ್ನು ಅದು ರೊಟೇಷನ್ ಕೊಡುತ್ತೆ ಓಕೆ ಸೊ ಟಾರ್ಕ್ ಕಾಸಸ್ ರೊಟೇಷನ್ ಸೊ ಹಿಯರ್ ವಿ ಆರ್ ಕನ್ಸಿಡರಿಂಗ್ ದಿಸ್ magnetic compass needle and this will rotate due to the torque acting on this magnetic compass needle. Clear? So next I need to know what is the deflecting torque here. Deflecting in the torque sense, right? So this magnetic compass needle will rotate due to the torque acting on it, right? So the rotation means or it oscillates means okay it is deflecting okay so deflecting torque magnetic field, right? So here deflecting torque on which deflecting torque on magnetic compass needle on needle due to magnetic field is given by like this. So here torque means it is tau. So deflecting torque is equal to, and we know what is that? It is M cross B, right? So N cross B. Here M is the magnetic dipole moment and B is the magnetic field, right? So in magnitude form I can write MB, it is sin theta, MB sin theta. So this is our deflecting torque. Okay, this is our equation number 1. So what is theta here? Here theta is the angle between magnetic dipole moment and the strength of magnetic field. Okay, so this magnetic compass needle has some magnetic moment. So this is theta is the angle between magnetic compass needle, that is the magnetic dipole moment of magnetic compass needle, and B. Here B is the magnetic field, right? So due to moment of inertia okay, so restoring torque due to moment of inertia is given by, so it is tau r. So restoring torque is equal to I alpha, where I is the moment of inertia of this magnetic compass needle and alpha is the angular acceleration. So alpha is the angular acceleration. Okay, so these are the things we need here, and this is our expression number 2. Okay, and next at equilibrium. So what is restoring torque here? For example, so this is my, just imagine this is my magnetic compass needle and I am giving some amount of torque here. So this is the actual representation of magnetic compass needle here. So this is my deflecting torque. For example, this is my deflecting torque. So deflecting torque is MB sin theta. So deflecting torque. So this is my deflecting torque. Okay. Restoring torque. Here restoring torque due to moment of inertia. Right. So this is the deflecting torque. Then restoring means it has to come to its original position. So if you remove magnetic field, then this magnetic compass needle comes back to its original position. So this is our restoring torque. For example, so this is magnetic needle and this is the deflecting torque due to magnetic field. This is the deflecting torque due to magnetic field. Okay, So at some point it's stay at that point only andre alli nitಕೊಳ್ಳುತ್ತೆ. Next again when you remove a magnetic field or uniform magnetic field, then again this magnetic compass needle comes back to its original position. So what is the torque there? That is called as restoring torque. So the restoring torque is this much. So restoring torque due to the moment of inertia. So then at equilibrium position, okay, so at equilibrium position that torque becomes, torque in the sense that deflecting torque is equal to, okay, at equilibrium deflecting torque is equal to restoring torque. Why? This negative sign indicates that this deflecting torque and restoring torque are in opposite direction. So they are opposite direction, right? So this is the actual position, right? Okay, so this is our deflecting torque and restoring torque means this comes back to original position, right? So here it is plus and this is negative. So this negative sign indicates that deflecting torque and restoring torque are in opposite direction. Okay, so clear? Next, what is deflecting torque here? Deflecting torque means deflecting torque on a needle due to magnetic field, right? So it is MB sin theta. MB sin theta. Deflecting torque is MB sin theta, and the minus sign that indicates deflecting torque and restoring torques are in opposite direction. So next, what is tau R? It is restoring torque, that is I alpha. So restoring torque is due to moment of inertia. Okay, here I is moment of inertia and alpha is the angular acceleration, right? Okay, so next one, sin theta, or theta is very very small, then sin theta becomes theta. Okay, so then MB, it is theta is equal to minus I alpha, right? Alpha is equal to minus MB theta divided by I. So alpha is equal to MB theta. So here this angular acceleration with MB theta is equal to minus I alpha. So I can write this expression. This equation can be written as like this: alpha is equal to minus MB theta divided by I. Right. So next, here we know that. What we know? We know that from our previous class. We know the angular acceleration of particle executing simple harmonic motion. Angular acceleration of a particle executing simple harmonic motion. Right. So what is that? What is simple harmonic motion here? Simple harmonic motion means, for example, this is your bob and you are giving some acceleration to this bob and it is going to extreme position and it is coming back to extreme position and then it is taking mean position and then it is coming back and going forward and next coming back. So this here acceleration is directly proportional to the displacement, okay, from an equilibrium position, and it is directed towards that position. Okay, it comes back to its original position, then it goes again to an extreme position, right? So we know that and we learned that in our previous class, right? So here we know what we know here only, that is angular acceleration is equal to minus omega square theta. Minus omega square theta. Okay, so substitute this in equation number, okay, I will take as 3. Okay, in equation number 3. Alpha value, substitute alpha value in equation number 3. So alpha is equal to minus mb theta divided by I. So what is alpha here? Alpha is equal to minus omega square theta. Here alpha is the angular acceleration. Okay, so here then omega square is equal to theta, what is minus m b theta divided by I. So this is minus is there, so minus minus get cancelled, then omega square is theta is equal to m b theta by I. Okay. So alpha is equal to, we know that alpha is equal to minus omega square theta. Okay. So next we know what is here. So alpha is equal to minus mb theta by I. So this is equation number 3, right? Right, equation number 3. On comparing equation number 3 and equation number 4, we get that. So these two equation represent simple harmonic motion. Okay, simple harmonic motion, right? So here the oscillations of magnetic needle are simple harmonic. Okay, so magnetic needle oscillates due to the torque acting on it. This equation 3 and equation 4 represents the motion is simple harmonic motion. Then the oscillations produced or oscillations of magnetic needle are simple harmonic. Clear? So next, by substituting this alpha in equation number 3, alpha is equal to such, then it becomes omega square is equal to mb theta divided by I. It is theta get cancelled, next omega square. So next I need expression of magnetic field here. So next it becomes mb. So, okay, it becomes like this. B is equal to what is it? Omega square I divided by m. Okay, so B I goes here and it comes to denominator side. So this expression is called as magnetic field in terms of angular frequency. Magnetic field in terms of angular frequency. And I know what is angular frequency here. It is 2 pi f. Let's substitute 2 pi f here. B is equal to magnetic field is equal to 2 pi f square, right? Whole bracket square, and this I divided by this m. Okay. So B is equal to 4 pi square, it is f square, and I divided by m. And I know 1 by T is equal to f. Reciprocal of time field is frequency. Okay. So next B is equal to 4 pi square, it is I, and mt square. Right? This mt square. Where T is the time period or period of oscillation of magnetic needle. It is a period of oscillation of magnetic needle. And I need an expression of time period here. By using that expression, I can get expression for time period or period of oscillation of magnetic needle. Right? So T square is equal to, okay, so T square is equal to, right, it is 4 pi square I divided by this Bm or Mb, right? Next, I need T here, it is 2 pi, okay, square, okay, square of this one, so it's 2 pi, next it is I by Mb, right? This I by Mb, yeah. So this is the expression for period of oscillation of this magnetic dipole or magnetic dipole. What is that? It is a period of oscillation. This expression gives us period of oscillation of that magnetic needle. So this is a magnetic needle. So this magnetic needle is our dipole. So this magnetic dipole is our needle here. So this needle has this much of time period. So this expression gives us the period of oscillation. Period of oscillation in the sense time taken to complete one rotation from final position to initial position to final position. So this is the time taken by the magnetic needle to complete one rotation. So this expression gives us exact period of oscillation. Next, I need to know frequency of oscillation here. I need to know what is the frequency of oscillation here. So F is equal to, we know F is equal to 1 by T. Okay, so reciprocal of time period gives us frequency. Okay, so this is 1 by 2 pi and it is mb by I, where I is the moment of inertia, where m is the magnetic dipole moment of given magnetic dipole, sorry, which magnetic compass here, and B is the magnetic field strength, right? So F is equal to this much. So this is the expression for frequency of oscillation of magnetic compass needle. Clear? So this is all about dipole in a uniform magnetic field. So first we need to know torque acting on the magnetic compass needle. So there are two types of torque acting on that. One is deflecting torque, another one is restoring torque. So deflecting torque acting on magnetic needle due to magnetic field, that is mb sin theta, right? Next I need to know restoring torque acting on needle due to moment of inertia, that is I alpha, where I is the moment of inertia and alpha is the angular acceleration, right? So next, at equilibrium, those two in the sense magnetic field, the torque due to magnetic field and torque due to moment of inertia, those two torques are equal but they are opposite in direction. Okay, so tau d is equal to tau r, tau minus tau r, so minus d represents that. So those two torques acting on magnetic needle are opposite in direction. Next we need to substitute that values and then get alpha is equal to minus mb theta divided by n. Okay, so this value or this expression is similar to angular expression of angular frequency in case of simple harmonic motion. In case of simple harmonic motion, acceleration is directly proportional to displacement. Okay, clear? So next, substitute that values and alpha is equal to this much. So these two, actually equation 3 and equation 3 represents that the motion is simple harmonic motion. Then the magnetic needle produces some oscillations there, or oscillation in the sense it oscillates back and forth motion. So then it oscillates like that, so that oscillations are in simple harmonic motion, or those oscillations are simple harmonic motion. Okay, next I need to know what is time period or what is the period of oscillation of that magnetic needle, and thus I need to know expression for frequency of oscillation of magnetic needle when we keep that magnetic needle in uniform magnetic field. So this is all about dipole in uniform magnetic field. Clear? I hope this is clear to you all. Okay, so next is expression for magnetic potential energy stored in the magnetic needle rotated in the magnetic field. Okay, so this is our magnetic needle. Okay, so this is magnetic field, this is the uniform magnetic field, right? And we are keeping that magnetic needle in a uniform magnetic field. So then expression for magnetic potential energy. Okay, so what is magnetic potential energy here? In electrostatic we learn electric potential energy. So here same as we are using magnetic potential energy. There in electric potential energy, that the work done in bringing unit positive charge from one point to another point in a presence of electric field. Similarly, here we are using magnetic needle. Okay, I am telling about this scenario. I am telling about this scenario and I am explaining everything about this scenario. Here, work done in rotating a magnetic compass needle to some extent, then coming back to original position. Okay, like this. Here work done in rotating a needle from initial position to final position. So here potential energy is given as work done in rotating a magnetic needle from initial position to final position. Okay, so here work done is equal to F into dx. F is equal to, next here it is displacement, force equal to and displacement, right? But here we are using magnetic potential energy is equal to integration of tau. Why tau? Because here tau causes the rotation of magnetic needle. Okay, tau and beta, right? So next, what is tau here? Tau due to magnetic field. Okay, so that is mb sin theta. This part is mb sin theta in case of magnetic field, the torque is mv sin theta. And next, in case of what? In case of electric field or electrostatic, we know that P sin theta. P sin theta. Well, P is the electric dipole moment, and then E is the electric field. Similarly, here magnetic dipole moment, and next is a magnetic field. Okay, here theta is the angle between M and B. M in the sense is the magnetic dipole moment, and this is our magnetic field, right? So next, by integrating this, we get minus mb cos theta. Integration of sin theta is equal to minus cos theta, right? So next, um. So there are three cases. Theta is equal to 0 degree. Okay, it is 0 degree. Then cos 0 degree is equal to 1. Okay, um is equal to magnetic potential, and which is equal to minus mb into 1. So which is minus mb. Um is equal to minus mb. So here it is minimum potential energy. It is minimum potential energy. And second case, it is cos or theta is equal to 180 degree. 180 degree in the sense, here for example, so this is our magnetic field, and this is, okay, this is S and this is N. Okay, here it is our B magnetic field, but here we see that this is N and this is S. This magnetic dipole or magnetic needle rotates to 180 degree. Rotates to 180 degree. Clear? It rotates to 180 degree. Then theta is equal to 180 degree. Then cos 180 degree is equal to, it is minus 1. Okay, it is minus 1. Then potential energy, magnetic potential energy, it is minus mb cos theta. So cos 180 is minus 1. So minus plus, it is plus mb. In the sense, it is maximum potential energy, maximum magnetic potential energy or maximum potential energy. And another case, that is case number 3, when theta is equal to 90 degrees. When theta is equal to 90 degree, then cos 90 is equal to, it is what? It is 0. So um is equal to, it is 0. That means 0 potential energy. 0 potential energy. So these are the three important cases. So this is the expression of magnetic potential energy stored in the magnetic field and rotated in the magnetic field. So this is the expression for magnetic potential energy. Okay. So there are three cases. One is theta is equal to 0 degree, and theta is equal to 90 degree, and theta is equal to 180 degree. We get 0 potential energy in when theta is equal to 90 degree, and we get maximum potential energy when theta is equal to 180 degree, and minimum potential energy. So minimum in the sense it is less than 0. So we get less than 0 value here. So that is our minimum potential energy. Right? So this is the about expression for magnetic potential energy. Okay? I hope this is clear to you all. Thank you.